Dr. Elishakoff, your role, and you may proceed, sir.
Yes, good afternoon. We are continuing our discussion about damped free vibrations. What is the topic number? 12. Okay. So I'm just reminding you this. You please do not write this. So we started with differential equation. This governing differential equation, the load f of t equals 0, so damping C is not 0. So we divided whole left-hand side and right-hand side by m, by mass. Here I got k over m, and here we got natural frequency squared. So had there been no damping, then natural frequency would be omega sub 0. Now this expression C over m we see the coefficient, and we are replacing it by another coefficient. Another coefficient is zeta, and this zeta is a non-dimensional coefficient. C is a dimensional coefficient. Zeta is non-dimensional coefficient, and this non-dimensional coefficient is introduced as C over m equals 2 zeta times omega sub 0. Now this zeta then equals, okay, from here, this expression equals 2 zeta omega sub 0. So zeta equals C over m and 2 omega sub 0. So this is a viscous damping factor or viscous damping coefficient. So this governing differential equation, and we reduced to this one. And then we looked for the solution in A times E in power st. So we substituted here and got characteristic equation. So this is a characteristic equation for S. And this is a quadratic equation. This quadratic equation has two roots, S1 and S2. So one is with plus sign, the other is with minus sign. Or we could take out omega sub 0 because of our convenient choice. Omega sub 0 is here squared. So we get out it here. So we get this minus zeta plus minus square root zeta square minus 1 times omega sub 0. If there is no damping, zeta equals 0, then this term becomes 0, and I'm getting here square root of minus 1, which means that this term is 0, this term is square root of minus 1. So we have purely imaginary roots leading to harmonic solution that we had before. Now there is another case, another extreme, when zeta is, so zeta was small or zeta could be very big. And this is, let me show this here, yes, so zeta equals 0, or, yeah. Now when zeta is great, zeta goes to infinity, then square root of zeta square minus 1 goes to be zeta, because this, in comparison with infinity, this 1 can be neglected. So then S1 goes to 0 and S2 goes to minus infinity. So that means that solutions are like this solution decays, okay? Because E in power S2t, so that is E in power minus infinity times time is 0. And the other one goes to 0 times t, or constant. Now in general, I think that we came to here, is it not? Or not? Did we get to here? I think that is where we stood. And we may want to write that in the general case, we have this situation. When we have A1 times E in power S1t and A2 times E in power S2t. And so I wrote down these expressions. I wrote down explicitly this A1 times E, or exponent, in power and this power is minus zeta plus square root of zeta square minus 1 omega 0 t, and then a2 with minus sign. And then I took out this in power minus zeta omega 0 t, and what is left inside the square brackets is sum of exponents multiplied respectively by a1 and a2. Any questions? Now, this representation is good for overdamped case. Overdamped case. Because I have here zeta square minus 1, zeta square minus 1. So when zeta is greater than 1, this is a very comfortable representation. Now, so for zeta is greater than 1, motion is aperiodic or aperiodic, non-periodic. Indeed, there is here e in power minus zeta omega sub 0 t, so something that will decay with greater time. But then there is this interplay with two constants, and some solution can go up and then go down. At infinity, it must go to 0. Indeed, this is damping. So physics suggests that once there is damping, then at times going to increasing times or going to infinity, the vibration should damp out, should go to 0, because system's motion is being damped out. So equations are predicting, so to say, correctly the physical behavior of the system, and I think that I succeeded to show you this figure where for various values of omega, it says omega sub n, but omega 0, solutions look like this. So at increasing times, the x of t decreases. Okay? Now we go to the other case, and the other case is critical damping. Damping is not greater than 1. Zeta is not greater than 1, but equals 1. So damping equals to the critical value. Okay, if that is the case, then please look, in the roots, if we have this square root from, this expression is vanishing. So therefore, minus zeta plus minus 0. So we get here, you may want to write minus zeta plus minus 0 I get, because this guy becomes 0. So therefore, both roots are coinciding. They equal minus zeta omega sub 0, or just minus omega sub 0, because zeta is 1. So we have double root. We have double root. So let us recall what expression for zeta reads. Zeta equals c divided by 2m omega sub 0. Critical value, zeta equals 1 means I substitute here zeta equals 1, so I get c critical. C critical equals to the c numerator equals to the denominator 2m omega sub 0. Or it equals 2 square root of km. So actually we should say as follows. We should say as follows. So we have these three parameters, m, k, and c. So imagine that m is fixed, mass is fixed, k is fixed. And imagine that c changes. For example, we put this system into some liquid which has either big viscosity or small viscosity, various types of viscosities. Then we can have three possible cases. One case that C is smaller than C critical, which equals 2 square root of Km. So look, please. Because we know M and K are fixed, we can calculate this. That's very easy. And this also. We calculate this number. This number. So then we could get C is smaller than CK, C critical, or C equals C critical, and that means equals 2 times square root of Km. And third is C is greater than C critical. Okay. For example, if K equals how much do I want? 4, and M equals 16, then C small, so then C critical equals 2 times square root of 4 times 16. So 2 times 2 times 4, so this equals 16. So C smaller than 16 underdamped. C equals 16 critically damped. C greater than 16 overdamped system. So we have three cases. Such cases are usually very, they are studied in much detail in the courses of ordinary differential equations. Okay, now let us consider borderline between cases in which zeta greater than 1 and zeta smaller than 1. And that is underdamped. Please write down underdamped system. It is neither 0 nor 1, it's in between. Underdamped system. Usually, so we cannot provide very big damping in the system. So usually systems are underdamped or slightly damped. Please write down underdamped or slightly damped. Slightly damped means there is some damping, so it's not 0, but it's not much damping. So it's slightly damped. Okay, then S12 equals minus zeta plus minus. Now I can actually, I know that here I had zeta square minus 1, but I know that zeta is smaller than 1, so I would like to write here, represent it differently. Minus 1 minus zeta square. Then it is a product, this expression is a product of, so again, I wrote square root of 1 minus, that is zeta square minus 1, is it right? Yes, zeta square minus 1. So zeta square so square root. Zeta square minus 1 can be written as minus Okay, 1 minus zeta square. So then this equals square root of minus 1 and times square root of 1 minus zeta square. So this guy equals I, and this guy equals 1 minus zeta square. So this is, of course, positive, because we said that zeta is smaller than 1. So that is what we write. So we get this imaginary unit, I. Okay? So just very simple note that even Newton, even Sir Isaac Newton, did not recognize square root of minus 1, called it untouchable. Okay? So, what Newton could not touch we will. Therefore, paying attention, I mean, in my courses very often I make this statement that when we don't know something, we should not be afraid of not knowing something. Even great person like Newton did not accept trivial things that we should know. So therefore, if a student in any university does not like square root of minus 1, I understand him. He's on the level of Newton. Okay, so he has some inner, he's still living in, so to say, 17th century, that student. But he's with Newton. He's not alone. He's with great people. So therefore, but bad thing would be if you stay with Newton and then don't proceed. That would be very bad. But if you understand that, okay, he and I are in the same company, now I have to move, because he does not have to, he's retired already, I have to find a job, so I must learn this. Okay, so what we get here then is as follows. So I get then minus zeta plus minus I, square root 1 minus zeta square omega sub 0. Then this, pay attention, minus zeta times omega sub 0 t, of course this is a in power st. So this can be taken out here. So I'm getting, look please, x of t equals a1 exponent of this expression, omega sub 0 t. So an a2 exponent with minus sign, this expression. And then there is e in power minus this zeta times omega sub 0 t. It's a long expression. A long expression. Now we have this not, okay, if you are done, or if not, tell me please. Now we have this natural product, like, okay, 1 minus zeta squared times omega sub 0. We have it here, and we have it here. So that is denoted as omega sub d. And this omega sub d has a terrible name. That must confuse. It is called damped frequency. So damped frequency is really oxymoron, is it not? Because damping is one thing, frequency is associated with free vibrations. But not only some of us are on the level of Newton, but others are trying to confuse us even more. That is what is happening. So terrible name, so damped frequency. So we should call it slang, actually. When you read it in the book or in the report, so you should remember at least, okay, this is a slang. It's not that the guy is crazy who talks about this, but this is a slang, scientific slang. So then, look please, this expression is written much easier. A1 in power I omega sub dt plus A2 in power minus I omega sub dt times this expression, in power minus z omega sub 0 t. Are we done with this? So I'm going to the next page. So I just rewrote this omega d again, and I did write here unsuccessfully. It's called frequency of the damped free vibration, or just damped frequency. Okay. Now we have this e in power I omega dt. Now here comes handy this Euler's formula. Maybe the most important formula in mathematics is like this. Okay, these two. So in power I alpha equals cosine alpha plus I sine alpha. So actually most famous formula is when I substitute alpha equals pi. So then I get e in power I pi equals cosine pi plus I sine pi. Oh, that is right now. And now sine pi naturally equals 0. This guy equals minus 1. So I get e in power I pi plus 1 equals 0. Okay, so this is a Richard Feynman. So this is the most beautiful formula in mathematics. Okay. So this guy, of course, is a Nobel Prize winner. Otherwise, we would not quote him. We're not quoting any person who is passing by, and he said this, and this guy said this. Okay? Now, what is interesting here is that 5 important constants, 0, 1, pi, I, and E appear together. They are tied together. So it's very nice. Things are interconnected. So 0, 1, pi, I, and E. Can I remove this page? Okay, so this is called Euler's formulas. E in power I omega dt equals cosine omega sub d. Please write down, if you write d as an index, sub d, not on the same level. T plus I sine omega dt, and here is minus. Now I'm actually substituting these formulas into my expressions. Do you have a question? No. Okay. So I wrote, look, A1 times this expression, cosine omega dt plus I sine omega dt, plus A2 with minus sign. Okay, once you are done, tell me and I'll go further. Okay, now we are going further. Please, here I have cosine omega sub dt, and here I have cosine omega sub dt. I'm taking that out. So what is left here is A1 plus A2. And here then I have sine omega d sub t. And then I have I times A1 minus I times A2. These substitutions probably have been made in many courses or in various courses, maybe in differential equations. Now this I'm denoting as C1, and this I'm denoting C2. And I'm getting C1 cosine omega dt plus C2 sine omega dt times e in power minus z omega sub 0 t. Now I also don't, maybe you may want to write it down, I don't want cos, okay, so this is fine actually, we could have left it here. So you can write down, we could leave it here. C1 and C2 should be found from initial conditions. And how many initial conditions we have? 2. What happens in the beginning? Displacement, beginning displacement is some value. So let me write it down. C1 and C2 from initial conditions. Say x of 0 equals alpha and x dot at 0 equals beta. Or example, x sub 0 equals, say, 2, x dot sub 0 equals 3. Okay? Then I will get, look please, here, x sub 0 equals, when I substitute 0, C1, this guy is gone because it's, so this is 1. So C1 equals 2. Okay? Let us just solve this problem indeed. Now derivative, we are calculating the derivative. X dot of t equals. So first of all, so it's a product. So I'm differentiating first this parenthesis. So will be minus C1 omega sub d sine omega sub dt, and then plus C2 omega sub d cosine omega sub dt. So I differentiated this, I leave it as is, minus z omega 0 t. Plus, then I'm leaving this square parenthesis intact, cosine omega sub dt plus C2 sine omega sub dt, and I differentiate this with respect to t minus zeta omega 0 e in power minus zeta omega 0 t. Okay, now I'm substituting 0, x dot 0 equals. This thing is gone, so I'm left with this, C2 omega sub d, and this is 1. This is also 1. Then plus C1. Okay, this is 1, this is 0, and this is multiplied by minus zeta omega sub 0. Okay, now this is 3, I said. But C1 is 2. So I get C2 equals 3 plus 2 zeta omega sub 0 divided by omega sub d. So I found C1 and C2. I just considered a very specific case. So as we see, okay, so I can write actually at the very end that it equals x of t. Let me write down in this C1. So C1 equals 2. 2 cosine omega dt plus C2. 3 plus 2 zeta omega sub 0 omega d sine omega dt in power minus zeta omega 0 t. So I finish. Then I put in the computer and I plot various curves. It's very simple. Okay, now I naturally would like this to be written in a, I don't want sine and cosine together. We would like to somehow reduce it to this form even more. So therefore I'm saying, let us multiply by square root of C1 squared plus C2 squared. So just write here x of t equals x of t. And please write here another representation. Another representation. So this was finished. I mean, we finished this. Now we write another representation, and we write here x of t. So I have square root C1 squared plus C2 squared. I just multiply everything by it, and naturally I have to divide it by it also. So I divide it also by C1 squared plus C2 squared, both terms. Now I can denote this guy, for example, by sine phi. This one. Look, please. This expression is smaller than 1 because C2 is divided by something bigger in itself, C1 square root C1 squared plus C2 squared. So this cannot be bigger than 1. Therefore, you may want to write, it makes sense to call it sine of some angle phi. So you have to write down this. This is very important. It's not just, it doesn't come from the sky. Because this quantity, C2 over C1 squared plus C2 squared cannot take values greater than 1 by absolute value, therefore I can call it sine phi. Now, if this is sine phi, then this must be cosine phi, because square of this plus square of this equals 1. So this square root C1 squared plus C2 squared is called A. So I get like this, then A times cosine omega dt cosine phi plus sine omega dt sine phi in power minus z omega 0 t. See, it's a long derivation. But good food needs a long time investment. This is not a junk food. Neither a fast food. Yes, sir.
E to the power negative phi, it's omega d or omega.
Here, no. This relies to this one, this expression.
I mean,
But power is in power minus z omega sub 0 t, as it was before.
sub 0. It should be sub d or
Should be?
sub d or sub 0.
No, I think that no. Sub D appears here, but here is omega sub 0. I will show you the previous. Because sub D was coming when we had square root 1 minus zeta square. So the square root 1 minus zeta square does not appear with this. It is separate. Omega sub 0. So now this is a product of cosines plus product of sines, so therefore it is cosine of the difference. Okay, according to the cosines formula. So then it is A, capital A, cosine omega dt minus phi, e in power minus zeta omega 0 t. See? In order to get something nice, you have to work. So we got a short formula, short, snappy formula. Any questions here? So what is phi? So cosine phi equals this. Or sine phi equals this. So C1 and C2 are found from initial conditions. And then we are forming this relation, and it is sine phi. From there we find phi. Then this phi is being substituted. Yes? Say it again? Yeah, phase shift. Phase shift. And now this whole business that we dealt with is called, as we know, the underdamped case. So what happens is as follows, please. So we have something which varies harmonically multiplied by something that decays exponentially. So that is what we have. Please write it down. We have a product of harmonic variation times exponential decay. Now this is very beautiful, actually, result what we obtained. Because, look, if zeta was 0, and this term is 1, and we get harmonic variation. So please write this. If zeta equals 1 if zeta equals 0 in the limit, then e in power minus zeta omega sub 0 t equals 1. So we get harmonic variation, only cosine. So this we knew from free undamped vibrations. Please write it down. Again, when zeta equals 0, e in power minus zeta omega sub 0 t equals 1, and we have harmonic variation. Now, this harmonic variation we had when we had undamped vibrations. So everything makes sense. When zeta goes to 0, we are coming back to our old friend, that is undamped vibration. Now, this formula is even more beautiful than it seems. Why? Because look, please. When we have damping, then like undamped vibrations are multiplied by something that depends only upon that depends on damping. Okay? When we do have damping, then undamping vibration is as if multiplied by something that decays exponentially. We could not anticipate this ahead of time, that there will be a product. We want to write down. This is a very profound thought. So when there is a damping, we get a product of two functions. One function is connected with a lack of damping. Other function is connected with damping. Yes, there is this omega sub 0, but omega sub 0 is actually a number, if you remember, yeah? Square root of k over m. So it has nothing to do with free vibrations. So omega sub 0 is a notation, nothing else. So we have a product, which is a very beautiful result. It could have been something else, maybe summation and products, or who knows what. It could have been something very monstrous expression, but here it is just a product. So this is like product of influences. Freedom is multiplied by decay. You see, if you don't take care of yourself, of freedom, then it decays. If you don't protect it, it is gone. And if you want, we could give such an interpretation to this formula. Okay, now this thing is provide an envelope. These are envelopes, something bounding the oscillations. Look, maximum here is 1. Okay, maximum of cosine is 1. But now, maximum of this whole thing is this one. Because this is smaller than 1, so maximum is then a times e in power minus zeta. So the curves plus minus a e in power minus zeta omega sub 0 t provides the envelope bounding the oscillatory response. Okay, clearly when t goes to infinity, x of t also goes to infinity because of this term. So that the response dies out, which represents the observed behavior in real systems. So it makes sense. This whole analysis makes sense. We don't get a nonsense out of our considerations. Okay, example, initial conditions, for example, x sub 0 equals 0. Initial velocity, initial displacement may be 0. Initial velocity may be v sub 0. And we could have various cases. Okay, so let us consider 3 cases. So we have x sub 0 equals 0. First derivative equals initial speed, initial velocity. So we consider 3 cases: zeta greater than 1, zeta equals 1, zeta smaller than 1. Okay? This is an example. So, zeta greater than 1. So x of t equals this long expression. As you see, to be an engineer should have a person should have a patience. To write this expression, it takes much time. And since we are rewriting this expression, it makes, if I'm spending so much time, I better also rewrite it correctly. Otherwise, if I will write instead of plus minus, then the whole work in the future will be totally bad. Patience and care. Now x sub 0 equals, we said 0. So this one is 0, and this one, this t is 0, so that this exponent is 1, and this exponent is 1. This is 1 also, so a1 plus a2 equals 0. So a2 equals minus a1. So from one condition, we reduce number of coefficients. a2 equals minus a1. So I will substitute this expression into my equation. So therefore, I can take out this a1 out. So it will be exponent minus exponent times this. So that is what my expression is. I just have one coefficient now, a1. If I'm going too fast, please tell me, then I will slow down. I will damp out. By the way, I would like to announce for those who are taking this course in FEEDS, please call me at 561-297-2729 and or send me an email at elishako@fau.edu. I would like to have your response, comments, questions, etc. Now we know that difference of exponents equals 2 times sinh function, hyperbolic sine function. Why I do all of this? Because I like to deal with less expressions and less quantities, etc. So 2a1 in power minus z omega sub 0 t sinh square root of psi square minus 1 omega sub 0 t. Now we calculate the first derivative. So when let us first look at it and then you write down. When I differentiate sinh, I get cosh. With this argument, when I differentiate argument, I get square root zeta square minus 1 omega sub 0. Then, and this stays intact, it appears here. Then I leave it alone and differentiate this guy, I get minus z omega sub 0 sinh. Okay, so that is this expression. So it's a combination of hyperbolic cosines and hyperbolic sines. Everything is extremely easy, actually. Just it takes some time. Otherwise, it's nothing special, nothing cumbersome. Everyone can do it. So we said that